So we are starting chapter 7, which is on linear momentum, and we will define each of the terms. So basically, what is momentum? We use this term in various ways in everyday language, and most of these ways are consistent with precise scientific definition. We speak of sports teams or politicians gaining and maintaining the momentum to win. So it has both a scientific meaning as well as a literal meaning. We also recognize that momentum has something to do with collisions, which you'll see in this chapter when we'll talk about conservation of linear momentum during collisions. For example, you observe the contact sports like rugby, and you also observe the contact sport like football. So we see players collide with each other and colliding and falling to the ground. We expect their momenta to have great effects in the resulting collisions. So generally, momentum implies a tendency to continue on course, or to move in the same direction as that of the speed, and is associated with great mass and speed. So whenever we think about momentum, we think about speed, we think about mass. So you're not wrong in thinking like that. Momentum is basically a product of mass and velocity. So momentum, like energy, is important because it's conserved. So momentum is always conserved, you have to remember, in all scenarios. Only a few physical quantities are conserved in nature, and that is why it is very important to study these, and it's very intriguing. Why is momentum conserved all the time? And the problems that we'll do will actually help us learn as well. So in chapter 7, we will cover 7.1, that is momentum and its relation to force. Then we'll also work on conservation of momentum, and then we'll work on collisions and impulse. The part 1 of this chapter will deal with these 3 sections, and then part 2 of this chapter will deal with 7.4, 7.5, and 7.6. That is all we are covering from this. And chapter 6 and chapter 7 are going to be for exam 3. All right, so we don't have too much content to worry about for exam 3. Chapter 6 is already done, and I hope you understood it clearly. If not, you should always come to office hours or let me know beforehand which problems you want me to discuss, and I can discuss them during the office hours. All right, so let's get started with momentum chapter. So basically, what is the definition of momentum? If we have to have a scientific definition, so momentum is basically a vector quantity, and symbolically it is represented by small p. So if we define it scientifically, it's consistent with most people's intuitive understanding of momentum is a large, fast-moving object and has greater momentum than a smaller, slower object. So linear momentum is defined as the product of system's mass multiplied by its velocity, and this is its symbolic representation. Velocity is a vector, and mass is a scalar quantity, but the multiplication of a scalar with a vector gives me a vector. And if you must have guessed that momentum is a vector though, but what are the units? So the SI units of momentum will be kg, and the units of velocity meters per second. Yeah, there's no shortcut form for this. The units of momentum, which is symbolically represented as p, is kg meters per second. No scientist name is involved with the kg meter per second for a change. So it's actually said that momentum is directly proportional to object's mass, and it's also directly proportional to object's velocity. And when we combine these two equations, we get this equation. So you have the first equation of the momentum. Thus, greater an object's mass or greater its velocity, the greater will be its momentum. If the mass is increased, the momentum will increase automatically because it's product of mass times velocity. And if velocity increases, momentum will also increase. If both increases, both mass and velocity increase, naturally momentum will anyways increase. All right. So why do we call it linear momentum? Because if we have an object over here, and suppose this is an object A, and it collides with another object B, then this object will transfer its energy to B, and they go in. This one goes in a particular direction in the linear form. So in this chapter, we are not doing two-dimensional momentum. I'm only restricting to one-dimensional motion, because when we go to two-dimensional motion, it really becomes complicated with angles and vectors in x and y coordinates. So I want to avoid that at this point. Towards the end of the semester, we'll just use one-dimensional linear momentum. All right. So let's take a look at an example. Here we say that there's a football player and so a football player and a football. So calculate the momentum of 110 kg football player running at 8 meters per second. So if there's a football player and it's running with a certain velocity, and the velocity is given by 8.00 meters per second, and his mass is 110 kgs, so we can find out what his momentum is, because we know that momentum P, it's a small case p, is equivalent to mass times velocity. Just by substituting the values, we can find the mass of the, you can say the momentum of the player, mass of the player if you want to be specific, is equivalent to 110 kgs multiplied by velocity, which is 8.00 meters per second. And once you multiply them, you will get 880, two sig figs. If we maintain two sig fig, 880 kg meters per second is the momentum of the player. It's a vector quantity because momentum always is directional. So then we talk about compare the player's momentum with the momentum of the hard thrown 0.410 kg football that has a speed of 25 meters per second. So we just found out the momentum of the player is 880 kg meters per second. How about finding the momentum of the ball that is coming through? So momentum of the ball will be mass times mass of the ball multiplied by the velocity of the ball. And so that mass of the ball is 0.410 kgs. But you must see that even though the mass is small, the velocity is 25 meters per second, and it will compensate for the momentum. So let's see. So very little mass compared to 110 kg, 0.410 is a very small mass. And even if we have 25 meters per second speed, we just want to see, is this momentum going to be bigger than momentum of the player? Unfortunately, when we multiply this, 10.3 kgs meter per second is the momentum of the ball. Clearly, momentum of the ball is lower than the momentum of the player. So by how much it is? So momentum of, you can take the ratio, momentum of the player divided by momentum of the ball is equivalent to 880 kg meters per second over 10.3 kg meters per second, and that comes out to be equivalent to 85.9. So what does that mean? That means momentum of the player is 85.9, which is roughly 86 times momentum of the ball. So momentum of the player is far larger than the momentum of the ball. So although the ball has greater velocity, the player has much higher mass. Thus, the momentum of the player is much greater than momentum of the football, just as you saw the results. So player's motion is only slightly affected if he catches the ball. And that's why he doesn't get hurt by the ball that is coming towards him, because the momentum of that ball is very low compared to the momentum of the person who's running. So then we move on to what is the relationship between momentum and Newton's second law. So how did I arrive at this formula? All this while I knew that Newton said that net force is equivalent to mass times acceleration. So what is this new formula that I'm getting? Or is it possible that I can get this formula from just Newton's second law? So let's try that. We know that mass times acceleration. What is acceleration basically? Acceleration means change in velocity over time. Is that okay? We can write delta t, change in time. So this becomes mass times, if I open the bracket, it becomes mass times velocity final minus mass times velocity initial delta t. So it seems that hidden inside Newton's second law is momentum equation, and this becomes final momentum minus initial momentum p naught divided by delta t. So does it not look like it is change in momentum? Final minus initial momentum is change in momentum over change in time, and that's exactly what we are talking here. So this is how we find out what is the relationship between Newton's second law and momentum. So force and momentum are intimately related. Force acting over time can change momentum. So if the time increases, then momentum can also change. And Newton's second law of motion can be stated in its most broadly applicable form in terms of momentum change. So momentum continues to be a key concept in study of small particles, atomic level and subatomic level particles, in another form of physics study, which is called quantum mechanics. So it has a lot of appeal there, which you may not be knowing. And so keeping that in mind, we can work on one more problem. So the units of the momentum will not change, and the units here still stay Newton. So do not worry about the change in formula. It's still Newton's. Force will never change its units. It's in any scenario, force will have Newtons as the unit. So let's take an example of tennis now. During 2007 French Open, Venus Williams hit the fastest recorded serve in a premier women's match, reaching a speed of 58 meters per second. Gosh, that must have been a real high impact. 209 kilometers per hour is a tremendous amount of serve. What is speed for the serve? What is the average force exerted on the 0.057 kg tennis ball? If this was the speed and that tiny ball, what must have been the impact on that ball? So assuming that the ball's speed just after the impact is 58 meters per second, and that the initial horizontal component of the velocity before impact is negligible, and that the ball remained in contact with the racket for 5 milliseconds, which means 5 cross 10 raised power minus 3 seconds. So what are you going to find out? You have to find out the average force. So what is the strategy that we can apply? This problem involves only one dimension because the ball starts from having no horizontal velocity component before impact. So Newton's, I'll have to do this problem behind in another slide. So Newton's law says net force is rate of change of momentum, right? And says rate of change of momentum. As noted above, when mass is constant, the change in momentum is given by delta P is equivalent to mass times, there's something weird happening with the pen and I just don't want this giving up on us. Delta V is the velocity. So that means mass times final velocity minus initial velocity. That's the change in momentum, right? And in this example, the velocity just after impact and the change in time are given by the equation that we have over here. So to determine the change in momentum, I will simply substitute the values of the mass of the tennis ball, 0.057 kgs, and change in velocity. The final velocity is 58 meters per second. Remember, he said that there was no, assuming the horizontal component of the velocity initially is 0. So the overall change in momentum is due to the contribution from the momentum right after it started. So 3.306 kg meters per second. I can actually approximate it to 2 sig figs, that is 3.3 kg meters per second. So I have my change in momentum here, and now the magnitude of the external force can be determined using the above formula, right? So F net is equivalent to change in momentum over delta T, and I already know my change in momentum. It's 3.3 kgs meters per second divided by the time, which is 5 milliseconds, 5.0 into 10 raised power minus 3, 10 raised power minus 3 seconds, and hence I will get kg meter per second square when I combine the units, which is nothing but Newton. So I get 661 newtons, 661 newtons. This is 3 sig figs, so I would like to keep the 2 sig fig scenario here, which is 660 newtons is the actual approximated value of the net force. And we used Newton's second law to help us get the net force involved. So here we have retained only 2 sig figs, keeping in accordance with the problem that was given. So this quantity was the average force exerted by Venus Williams racket on the tennis ball during its brief impact. So that's a good amount of force. Note that the ball also experienced the 0.56 Newton force of gravity, but that force was not due to the racket. So you don't have to consider what was the gravitational pull. We don't include that. Okay, so we could also have done this problem alternately by simply doing F net is equivalent to mass times acceleration. We could have found the acceleration value. It's one and the same thing, either doing it this way or that way. The acceleration could be found from v minus v naught over t. We had all the quantities. A could have been determined because we had the initial, the final, and velocities, and also the time given because v is equivalent to v naught plus at. I could find A as v minus v naught over t. So 2 different ways of doing this, but we are applying the momentum approach here because we are trying to show it the other way around. This kind of force Newton's second law with F net is equivalent to mass times acceleration is already understood by us. All right, so let's move on to another example. This is basically an example from your textbook, and there is a person is washing the car, and you have to find out what impact is applied, how much force are you applying in order to clean this car. So you take a little while and try and understand what's happening here. You can always pause the video if you're watching it live, then also you can pause. But if you are not watching it live, this is a recorded video. You can always work simultaneously with me and then do the problem as well. So we have water hose here, which is sending out a really high speed jet to wash the window panes of the car, and the momentum is given as water leaves the hose at the rate of 1.5 kgs per second. That means the mass of the water, because it's not, why is this strange unit given, 1.5 kgs per second given? It's basically, we cannot find the mass of one droplet of water. We always measure it, how much water is falling or coming out of the rate of mass coming out of the hose. So kg per second is a rate of mass. So it's mass per unit second, and the speed with which it is coming out is 20 meters per second. So you are asked to find out the force that is exerted on the window pane by this water. The water leaving the hose has mass and velocity both, and so it has a momentum, and you can simply find it by using F of net is equivalent to mass times acceleration. But we know that in momentum we represent it simply by change in momentum, over time. So we will use this equation because that's our purpose here. We are in momentum chapter, and we want to find out using momentum formulas. P of final minus P of initial. So change in momentum always means final minus initial over change in time, delta t. Do I know the initial momentum? The final momentum is 0 because it's striking and it's coming to rest on the window, so final momentum is 0. The initial momentum is given as do we really have, yeah, it is shown that we have 1.5 multiplied by mass, that's the mass, 1.5 kg per second multiplied by 20. So how much is that? That becomes 30 minus 30 kgs meter per second. That's the momentum, because your velocity is 20 and the initial velocity with which it is coming out is 20 meters per second, multiplied by 1.5, which is the mass coming out, makes it 30, divided by change in time, it's per second. That's why it's written mass per unit 1.5 kgs per second. That means we are calculating per second, so 1.0 seconds, that's the time given. So that shows us the net force is negative, it's minus 30 newtons. All right, and the minus sign indicates that the force exerted by the car on the water is opposite to the water's original velocity. That's all it means, because momentum is a vector quantity, and the car exerts a force of 30 Newton to the left of left to stop the water. So by Newton's third law, the water exerts a force of 30 Newton to the right of the car. So the magnitude of the force is 30 Newton. The sign is just because it's the force is exerted in the opposite direction to the jet. All right, so this is how we solve momentum problems using Newton's second law. Time to solve some textbook problems, and here I'll be also posting the entire handout for your chapter 7. So we have a constant friction force of 25 newtons acts on a 65 kg skier for 15 seconds on level snow. So there's a skier on his skates, okay, and the mass of the skier is given as 65 kgs. And a constant friction force is applied. So he's going this way, although I would say the snow would be less friction, but still there's a force of friction applied, and we have to find out what is the skier's change in velocity. So we will use the Newton's second law, which says F of net is equivalent to change in momentum over time, change in time. But the change in momentum can also be rewritten as mass times final velocity minus initial velocity over change in time. And therefore force vector multiplied by delta t vector is equivalent to mass times v minus v naught. So we have to find out that change in velocity, and I can easily call this as m into delta v and f into delta t, which is the time. Sorry, t is not a vector. Okay, so I have to find delta v. So divide both sides by m, we get f into delta t over m. So go ahead and substitute the values. We have been given, we actually have, if the skier moves towards the right, the force of friction is going to be in the opposite direction. So if this is the force of friction, which is in the opposite direction, so I should have a minus sign here because the skier is going this way. The force of friction is in the opposite direction, hence we will put a minus sign with this. So F of 25 newtons multiplied by your mass of the skier, 25 newtons multiplied by time, that is 15 seconds, and divided by mass is 65 kgs. I end up getting the change in velocity negative value, which is minus 5.8 meters per second, and that's because it's he's moving in this direction. The change in velocity is in the opposite direction, hence minus sign only indicates direction. Minus sign only indicates direction because momentum and force both are vector quantities. So next topic that we study in momentum chapter is conservation of momentum. Momentum is always conserved. We briefly talked about it, but I would like to give a complete detail on this one. So momentum is an important quantity because it's always conserved in all forms of nature, yet very little is known about it. So it is always possible to find a larger system in which total momentum is constant, even if momentum changes for components of the system, but on a broader scale, momentum is always conserved. If a football player runs into the goalpost in the end zone, there will be a force on him that causes him to bounce backwards. So the sum total of the momentum is always conserved. Another example is that the earth also requires conserving momentum because of the force applied to it through the goalpost. So basically, momentum before the contact and after the contact will always be same. So that is what is meant by conservation. So basically what happens here is, if I have two balls smashing into each other, there is a ball A. If you have played pool or billiards, it's also called billiards. Pool we call in America and billiards we call in Europe. So if two of them are colliding with each other, there will be a time when they will contact, and after contact they will go in their respective direction. So we say momentum before. So MAVA prime is the momentum of the ball A before collision, and MBVB is the momentum of ball B before collision. So sum of momentums of two objects before collision must be equivalent to momentum of ball A after collision and momentum of ball B before after collision. So that VA prime means after. This is the speed after they collided. So it's not the same as VA and VB. So you must note these. It's in your textbook. VA prime. This means before, and this means after. Same goes for VB and VB prime, before and after. By the way, after collision. Okay, so you just have to remember this is the basic rule. Conservation of momentum is existing all around, and we will try and solve some problems based on that. So if we see the two carriages of a railroad, and we assume that their mass is same, so one was at rest and one was in motion. This can happen. So understand the scenario. So carriage A is in motion, carriage B is at rest. Carriage, after collision, both of them get stuck together, but we still say that the total momentum of the system must be conserved. That means if carriage A has mass ma and its initial velocity was va, then this is the momentum of carriage A before collision, and mb vb is the momentum of the carriage before collision. That must be equivalent to, now these two became one quantity because they're joined and they are going together with combined speed. Then I cannot write MAVA prime anymore plus MBVB prime anymore, because they are not separated out, they are together. So I have to modify this equation. This is a typical scenario where objects after collision combine. So the masses are combined now. We add them up, MA and MB, but they are moving together in this direction. So then we call this as combined speed. So combined speed of VA and VB, and we write it as prime. So prime is an indication that it is after. So in the next slide, we'll go ahead and find out what is the combined speed of these carriages. So we are assuming these are railroad carriages and mass of A must be equivalent to mass of B. All right. So we will go ahead and write the law of conservation. Law of conservation of momentum. Which says momentum before collision MAVA plus MBVB which is before collision for both of them, must be equivalent to momentum after collision. Now we know our scenario, we know that they're combined, so we will write MA plus MB, MB is V prime multiplied by V prime. So that is the momentum equation for us here. And now he's not giving us, I'm not sure if he's giving the mass. So do we really need the mass? If MA is equal to MB, how will you solve this? So we have to find out basically if MA is 10,000, this is the railroad carriage, so let us assume that the mass is 10,000 kgs and both of them have the same mass, so I can always say MB is also 10,000 kgs. Okay, so you have to find the combined speed of both of them when after collision. So divide both sides by MA plus MB. So MA VA plus MB VB whole divided by MA plus MB is equivalent to V prime. Now remember that VB is stationary, so 0 comes over here. So now my equation is shortened, it becomes MAVA over MA plus MB is equivalent to V prime. Go ahead and substitute the values. You can substitute 10,000, 10,000. You can even take out common, and it could be done differently as well. But anyways, I don't want you to get confused. You can substitute 10,000 kgs multiplied by VA, which is 24.0 meters per second, whole divided by 10,000 plus 10,000 is 20,000 kgs. And then you can find out what is the V prime. So do your math and find out what it comes out to be. This is actually going to be very simple. You don't even need math calculator for this. If you see, this is 10,000 and this is 20,000, that will be 2 and 24 becomes 12. So your V prime, the speed with which both of them are going together forward, is 12 meters per second. So this is how you will be able to find how to solve problems with combined masses or not combined masses. So let's say what is happening in the second part. Even in momentum is also conserved when rockets are fired. So basically we get initially when they were at rest, there is no motion, momentum is 0. But once we fire the rocket, the gases come out in this direction and the rocket moves forward. So there is a momentum before is 0 because they were not moving. So that must be equivalent to momentum after. So momentum of the gas plus momentum of the rocket, it's after the gases exploded out. So that's how you can understand that. Even when they are combined together and they internally explode, we can still have momentum of conservation. So next we are going to solve another problem based on a recoil. So it's a rifle. Rifles, when you fire from a rifle, you are observing the momentum, conservation of momentum even there. Okay, so we have been given that calculate the recoil velocity of a 5 kg rifle that shoots out a 0.020 kg bullet at a speed of 620 meters per second. So it's an interesting problem. Initially, both of them are at rest. And later on, once you fire, both of them come into action. The rifle moves backwards, but the bullet moves forwards. So how should I write my conservation of momentum equation? So the conservation of momentum can be written as, if I name them as momentum of the bullet and momentum of the rifle. So it would be easy to write that way. So m of the mass of the rifle and velocity of the rifle, this is beginning, plus mass of the bullet, velocity of the bullet before collision, must be equivalent to mass of the rifle after, velocity of the rifle after, plus mass of the bullet after, velocity of the bullet after. Hope you understand that. In the beginning, when nothing is shot out, both of them are 0. So that will be equivalent to m mass of the rifle, velocity of the rifle, plus mass of the bullet and velocity of the bullet. So some things have been given to us. Mass of the rifle and both of them are given. Mr is given, mb is given, and vb is given. We have to find out the recoil velocity, because recoil velocity is if you if you fire a bullet, you feel that the gun goes backwards, so that's the recoil velocity. So let's substitute the values and find out what happens to the recoil velocity. Rearrange the terms here. We want to find the recoil velocity. Therefore, mr vr prime must be equal to minus mb, the mass of the bullet, vb prime, the velocity of the bullet in the forward direction. Therefore, vr prime can be obtained by dividing both sides by mr. These are the algebraic steps. So you have your mr, substitute the values for all of them, and you get the recoil speed as, it's a smaller speed, minus 2.5 meters per second. The negative sign is because the recoil velocity is towards the left, while as the bullet velocity is towards the right. And you can see the comparison. The velocity of the bullet coming out is 620 meters per second, but the recoil speed is only a little bit. The gun feels a jerk backwards. That's minus 2.5 meters per second, which is not a lot. So you keep these scenarios in mind because you'll have to solve many problems. And then we go ahead and solve problem number 3 from your textbook, which says that a 7,150 kg railroad car travels alone on a level, frictionless track with constant speed of 15 meters per second. A second 3,350 kg load initially at rest is dropped onto the car. What will be the car's new speed? So basically, there is a railroad car over here, and initially it was traveling alone on a frictionless track with a speed of 15 meters per second, and suddenly from somewhere 3,350 load is dropped on this, and then the dropped part is also going along with this cart, so they are combined now. Initially the bullet is at 0 speed, and then it falls on here, and the cart was moving. So we can work on this problem knowing, now that we know the scenario, what is happening. So consider the horizontal motion of the objects. The momentum in the horizontal direction will be conserved. Let A represent the car A and B represents the load. So because we like to write the equation as MA VA plus MB VB is equivalent to, now that the load and this load of 3,350 kg is also inside the truck. It's not going anywhere. So they are combined and they have a combined speed v prime. So we can go ahead and find out what was the combined speed. Divide both sides by ma plus mb. So we have mass of the railroad, velocity of the railroad in the beginning, plus mass of the bullet and velocity of the bullet in the beginning, whole divided by mass, the two masses together. That will be equivalent to v prime. We are dividing both sides by ma plus mb. So we said the load vb is at rest in the beginning. This is the load, but the cart was moving. We have va, that is the railroad car, and it had a speed of 15 meters per second. So we go ahead and substitute the values of the masses, and incidentally this term is gone because vb is 0. So we are left with ma, mass of the railroad, velocity of the railroad initially, divided by sum of the masses of both railroad and the load is equal to v prime. Go ahead and substitute 7,150 for ma and substitute 15.0 meters second for the railroad track or railroad car, and add the two masses. Now that the first mass is 7,150, mb is the mass of the load that is falling, 3,350. Okay, so when you add them up and work on the algebraic expression, you get v prime equivalent to 10.2 meters per second. Okay, so that solves your third problem. This is also based on conservation of momentum. If you look at these formulae, you are using conservation of momentum everywhere. So once again, we can work on one more problem, and then we'll call it a day. 110 kg tackler moving at 2.5 meters per second meets head on and holds on to an 82 kg halfback moving at 5.0 meters per second. So this is the favorite sport of Boston, and we should definitely work on this problem. What will be their mutual speed immediately after collision? Sad that we lost Brady. Now we don't have him, but still the sport continues. And we will use the conservation of momentum, saying that initial momentum must be equal to final momentum. And the initial momentum is comprised of, if we name the tackler as A and the halfback as B, then we can say MA. We'll use the same scenario, MA VA plus MB VB must be equivalent to, when they are combined together, MA plus MB, and their final speed together, V prime. So if you were able to do the previous one, you have to understand both of them were coming like this, and then after some time they were together in the tackle position. So they will either go this way or that way. Let us find out. If we get a negative sign, that means they are going westward, and if it goes this way, that is positive. So let us see what's happening. So we will rearrange the terms, and just like in the previous problem, we found out MA, divide both sides by MA plus MB, VA plus MB, VB, whole divided by MA plus MB. Okay, I just realized I've been using a lot of red. Let me pick my favorite color, that is green. So I get to substitute the values now, and it's up to you which one you are choosing, which direction you are choosing. If I choose the halfback here, he's going in the positive direction, and the tackler in this direction. So the tackler is coming in the negative direction. So remember the direction of speed and what value you're, what sign you're putting for that. That is the most important part in getting these problems right. So this is the tackler. You could do the vice versa. You could put the halfback here and tackler this side, but you have to remember speed on this side will follow. If the speed is this way, you will use minus value for that, and if the speed is this way, then you'll use plus value for that. So now we'll take care of that. So mass MA 82 kg halfback multiplied by the speed VA. So halfback is going in the positive direction, so I will put a speed of 5.0 meters per second with that, plus mass of the tackler 110 kg. But I'm going to be very careful when I'm writing the speed. I will write minus 2.5 meters per second because the tackler is coming in the negative direction. Divide that by the sum of the two masses, 82 kgs plus 110 kgs. When you add up all of this, remember there's a minus sign here, the minus sign will come out, and you end up getting 0.703 meters per second, or if you want two sig figs, it's 0.70 meters per second is the speed, the combined speed of them. You must have understood what is happening here. Because the halfback had a higher speed, it pushed it, both of them went in the positive direction because your final result came out positive direction. So the number will tell you which direction it went. If this was minus, we would know that they are going westward. Okay, so keep in mind the sign will tell you the direction. They will be moving in the direction that halfback was running before the tackle. So even if you had switched the direction between the halfback and the tackler, if you had kept the halfback here, then you would have gotten minus sign. So basically, whatever is the direction of the halfback is the direction in which they are going to go because of its higher speed, double the speed. So the last problem before we exit out for today is calculate the force exerted on a rocket when the propelling gases are being expelled at a rate of. It's the same thing that we did for the water hose, because we cannot find out the mass of the gas that is coming out because it's coming out per second. So that is why we use a rate of mass. This is called rate of mass or mass per unit second. So it's very hard to say how much gas is coming out per second. That's why we say, okay, 1300 kgs are coming out per second. We can't tell how much gas is coming out for the whole time. So, and it's coming out with a speed of 4.5 meters per second. 4.5 into 10 to the power of 4 meters per second. Obviously, this is a rocket. So we are, the force on the gas, calculate the force on the gas. So this must put you to thinking we are talking about force on the gas must be change in momentum over change in time, because we are using the Newton's second law version of this formula of mass. Mass times delta V over delta T. You must understand delta P means mass. Why did I write mass into delta V? That is because delta P means mass times final velocity minus mass times initial velocity is change in momentum. Final momentum minus initial momentum But if I take m out, I can write this as m times v minus v naught, which is nothing but m delta v. That is why I can write delta p as m into delta v. All right, so something has been provided here. If I rewrite this delta v, calculate the force exerted on the rocket when the propelling gases are being expelled at rate of this with a speed of 4.5 into 10 raised by 4 seconds. Basically, initially the gases were not expelled out, so initial velocity was 0, but later on the gas, when it came out, was ejected with a speed of 4.5 into 10 raised by 4 meters per second. And I am deliberately putting mass over time together because that is what has been already given. It's 1300 kgs is the mass per second. That means delta T is 1 second over here. Okay, so now I can find the force on the gas. That is 4.5 is the change in velocity, meters per second. Mass is 1300 kgs over 1 second, which is what it means by 1300 kgs per second was already given. So you go ahead and put it in the calculator and solve it. You will find the force exerted by the gases is 5.9 into 10 raised by 7 newtons. That is a large force. It's in the same direction as the velocity. In the same direction of the velocity of gases. So the gases are coming out in the back direction and motion is in the forward direction. So you have to remember the force on the rocket is the Newton's third law pair, equal and opposite. In the rocket, when the gases are coming out, the thrust or the force is in the forward direction. But in this particular problem, you're only finding out the force on the gases, not the thrust. If you were to find thrust, you would put a minus sign here because it's going in the opposite direction. So 5.9 into 10 raised by 7 is in the opposite direction of the gases. If you are trying to find out the force on the rocket, the force on the rocket will be up. The force on the gas is in this direction. Lastly, we'll find out, this is section 7.3, collisions and impulse. During a collision, objects are deformed due to large forces involved. So for example, if a car crashes, so once a car crashes, what is happening? You see the airbag comes out, and for a large force, in order to minimize the impact, we increase the time during which the impact will be experienced by the cushion coming out, the airbag coming out. That actually reduces the thrust. So that force that we experience for a short interval of time is called impulse. And I'll briefly describe it here. What is the basic meaning of impulse here? So impulse is also change in momentum, but it is a fast reaction. The process is really fast. Just like collision happening, if the two cars are colliding, there will be a dent, okay? But if there was a sponge here, or if there was a big foam board placed here, the impact will be less because you're increasing the collision time. And by increasing the collision time, you're reducing the impact force. That is why we have airbags in the cars. And the impulse tells us that we can get the same change in momentum with large force acting for a short time or a small force acting for a longer time. This is why you should bend your knees when you land. This is why airbags work and why landing on a pillow hurts less than landing on a concrete. Just think over this. We will sign off here, and I want you to actually, we'll work on the problem number 15 later. We'll call it a day and read through section 7.1 through 7.3, and once you get a chance, work on this problem on your own. Think about this problem. There is a 0.145 kg baseball pitched at 31 meters per second, and it is hit on a horizontal line drive straight back at the pitcher at 46 meters per second. We're talking baseball here. If anybody is a baseball fan, you should definitely do this problem before we meet next time. If the contact time between the bat and the ball is 5 milliseconds, calculate that force. So these are all forces exerted for very brief interval of time, and you can use the impulse formula for this one, and keeping in mind that impulse always means change in momentum is equal to force into distance. We call this as impulse. All right, and change in momentum basically means m into delta v. And you can find the delta v where m times v minus v naught is the delta v and force into delta t. So that equation can be rewritten like this, because change of momentum means this. He is giving you 31, he is also giving you 46. After the impact it turns 46, so final v is given, v initial is given, mass is given, time is given. Go ahead and solve for the force, where the force, then if you rewrite this equation, it's simply rate of change of momentum over time. This was derived from Newton's second law. So just to let you know, the answer is 2230 newtons towards the pitcher. So please solve this one, and I'll upload other problems also on the worksheet. So have a good one and see you next time.